Now, we are going to look at Doppler effect quickly. And Doppler effect is a section of waves, sound, and light, which we started from grade 10. But our focus mainly would be on sound. So before we even get into all the nitty-gritties of that, I want us to quickly take a quick drive back to grade 10 and 11. All right, what do I mean by going back to grade 10 and 11? This is very, very important. All right, so we're quickly looking at general knowledge on waves. We are going to redefine certain concepts because we're going to need it as we go on. All right, so the first thing we want to quickly look at is the keywords. What is the frequency of a wave? All right, the frequency of a wave is the number of complete cycle or vibrations per second. That's very important. Every time we talk about frequency, please think of number. Every time we think about frequency, please think of a number. This is very, very key. I like to rebuild some foundation, which is very, very important. Okay, so we started by looking at what a wave is. We started looking at the components of a wave. Just 1 second. Okay, all right. Now, the next thing to look at is period. Period is the time taken for one complete wave or vibration to pass through a point. Oh, there's something I forgot to do. Just try to squeeze it in for me. What is the unit of frequency? I like to just quickly deal with that. Unit is hertz. What about period? We said time taken, so the unit is seconds. Okay, very quickly there. Then I'm just doing a quick revision because I need it. We have the relationship between frequency and period. All right. The relationship between frequency and period, we know from grade 10, not going to waste time, that F equals to 1 over T. This is very, very important. And from there, we can also say T is also 1 over F, whichever way. That's very important. We're going to need all of that. Okay. Our third thing that I want to look at would be wavelength. 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 And we would define wavelength as the distance between two successive points on a wave that are in phase. Two successive points that are in phase. Or if I look at a longitudinal wave, then I can say the distance between successive compressions all right, we just want to quickly build, very, very important. And the unit is in meters because we're talking about length. And what is the symbol? The symbol is lambda. We're looking at general properties that we are supposed to bring in from grade 10, pass through grade 11, and finally establish in grade 12. Okay, I hope everybody's good. And all of these definitions are examinable. Please don't just know Doppler effect, wow, 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 and say you are done. No. You have to remember all of this, and I'm going to be linking all the concepts together. So follow me as we build. Okay, very, very crucial that you follow me as we build. All right, now let's talk about the next thing, wave speed, which is basically the speed of a wave, right? How fast or how slow a wave is. And because we're saying speed, we're actually saying it is the rate of change of displacement with time. Okay, so the speed of a wave can then be set to be the rate of change, okay, of distance, and therefore speed will be what? Distance over time. And basically, I'm not going to go into the grade 10 part of it, just going to go into the formula that we ought to know. So V, we now know that V in grade 10 and 11, we did this, is equal to F lambda. This is very, very crucial now. We're now starting to hit the main part of the lesson. This is very, very important. So we know that speed, which is measured in meters per second, frequency, which is measured in hertz, and that which is measured in meters. I don't know if you see, look at what I did here. So an examiner can actually ask for the equivalent unit of speed. Can you see that my speed, meters per second, can be measured as hertz meter? This is called equivalent unit. And you need to learn this skill across all the topics of physics by using units of the variables that we are dealing with. I'm hoping that we will come out, as you come across multiple choice, which is what many of us don't do. We just run straight to question papers. Please practice multiple choice. You're going to come across this type of skills. So this is called the skill of physics, equivalent units. If you watch any of my lessons, you will always see I will always talk about equivalent units. And it's very simple. Use the formulas. Again, this is what I mean. This is speed, meters per second. But speed is F times lambda. What is the unit of F? Frequency is hertz. What is the frequency of that? So an examiner can hide, because I can produce meters per second from here. Because if you look at your hertz, which is frequency, it is this. So it is 1/second. Oh, by the time I bring that back in here, so it is m/second, which is that. So take note of equivalent units. It's just a skill that I need you to know. All right, let's move quickly. Now, having said that, V equals to F lambda, I'm going to continue from here. All right, since V equals to F lambda, it simply then means F equals to V over that. If I do change of subject, and that is another skill I want to quickly put in your hands, another skill of physics. All right, so we're going to say that frequency is inversely proportional to the wavelength if the speed is constant. I know many of us just say inversely proportional. Please, whenever you say inversely proportional, there must be a constant variable. We miss that mark a lot. So F 1/lambda only at constant what? Speed. And what does this mean? As the wavelength increases, the frequency decreases. As the wavelength increases, frequency, don't forget what frequency is. Frequency decreases for the same wave speed. For the same wave speed. As frequency increases, or as the wavelength increases, the frequency decreases for the same wave speed. I want to show you what I mean here. I'm just going to use these green lines as my quick guide. All right. I'm sure you all still remember this type of things. Okay, if I look at that, let's call it A. I want you to see this, and this is examinable. They want to test, what you know. If I look at this, I'll use white. This becomes the wavelength of A. From the crest to the crest becomes the wavelength. And you would notice what I have here. I actually have how many waves would you see if I ask you, let's say this is 1 second. Let's put a timer here to say, this is my time. And we put 1 second here. Remember we said frequency is the number of waves that passes through a point in 1 second. So I have 1 wave and half. So 1.5 waves in 1 second. Now look at the wavelength of that. If I decide to increase the number of waves, check something here. I'm going to use a yellow one so that you're not confused. I'm keeping my amplitude the same, but I decide to increase the frequency of the wave. Look at the yellow one. And I'm going to use this. That's the wavelength of B. For the white one, we said frequency is what? 1.5, right? 1.5 hertz. If I then look at the yellow one, how many waves would you see here? Look at this. 1, 2, It's actually 2.5. What can you then tell me between the wavelength of A and the wavelength of B? Let's do this. Let's do this. Let's use a little table so that we can compare. I want us to compare A and compare B. We're going to compare the frequency and we're going to compare the wavelength. All right? You would notice that the frequency of A is lower than the frequency of B. All right? So I'm going to say low frequency, high frequency, looking at the values. But look at the wavelength. What can you say about the wavelength of A and B? Can you see that A is longer? Long wavelength and short here. I want you to see that we have just proven that F is inversely proportional. As the wavelength increases, the frequency does what? Decreases. So waves with long wavelength have low frequency. Let's put that note. If you have space, just put it here. Waves with long wavelength have low frequency, and waves with short wavelength have high frequency for the same wave speed. This is important before we even start your Doppler. I know many of you are done with Doppler or close to done, or some of you are just starting, but this is important before we even talk about listener and source and all of that. Okay, so this is very, very crucial. We're looking at the foundation. Let me know if we are okay, if there is no question, so we can move forward. If there's a question, we can quickly deal with it if there is any question. If you're okay, just give me a thumbs up and let me know that, all right, I think I'm still good and I'm still here. Awesome. Awesome. So a quick one is to let you know that examiners these days are moving away from you just reading and rewriting. No, applications are now involved, and this is application. Ntando, talk to me.
So how do you determine the wavelength of the graph by just looking at it?
You look at the distance between two successive points. So look at this one that are in phase. That's the crest to another crest. That's a wavelength. Did you see that right? I can also measure it from here. Look at this. It's still the same length to that. Exactly same point again. I can measure it from here. Look at your wave is coming down here, right? So it goes down, it goes up. Where is it going down again? There. That's another wavelength.
Thank you.
You are most welcome. All right. So now let's move into comparing the frequency and the wavelength when we have objects that are moving. So now this is now us going into what Doppler effect is. So we don't start with just Doppler is 1, 1, 1, 1, 1. No, it will not make sense. First, we start by going through frequency, period, wavelength, wave speed. We look at the relationship. Remember, the speed must be constant. Now, we can then look at the concept of Doppler. Okay, guys, 1 second. All right, now I want us to look at something because I want you to understand what this guy called Doppler observed. So, Doppler started measuring some important things. So, this was what he did. Look at this, guys. If I have a dot there, and that talks about the source of my sound waves. If my source is stationary, what will happen is this. My source will produce sound that will travel at equal distance and equal speed. Check that. That's what I'm going to have. So if I have a source that is producing sound waves, I want you to see something here. If my source is not moving, a stationary source, let's have a guy here, which we'll call a listener, listener 1, and let's have listener 2. With all of them stationary, this is what you will observe. The sound will reach both listeners at the same speed, because they are all stationary. So we're going to start from this. All right. For a stationary source, stationary means not moving, and a stationary listener, the speed of the wave is constant. The frequency released from the source is the same as observed by the listener. Remember, let's put hashtag there. Stationary. Stationary source and listener. Stationary source and listener. I'm going somewhere with this. You'd listen, just listen to me, and because I'm going to come back when I start applying. For a stationary source and a stationary listener, the speed of the wave is constant, all right? But that's not the main thing. The frequency released from the source is the same as the frequency, because both of us are stationary. The number of waves per unit time that the source releases is exactly the same number of waves that the listener would observe. That's point 1. Point 2. If the source and the listener move in the same direction, at the same speed, the frequency released is also the frequency observed. Put a hashtag here. Same traveling speed of source and listener. Example, the ambulance and the driver. Example, an ambulance and a driver. The ambulance and the driver are traveling at the same speed. The driver cannot travel faster than his ambulance to say, I want to put off the fire quickly. Ambulance is too slow, so I want to, So they are both moving at the same speed. What happens? The number of waves that is released per unit time by the ambulance siren will be the exact same. So it's not going to change. And it's just practical. If you are standing by the roadside, you would hear something different. But the driver of the ambulance is hearing the same thing from start to finish. Wow, 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 wow. Like that. Why is that so? The driver and the ambulance are traveling at the same what? Speed. So the frequency released is the same as the frequency of the. At this point, there is no Doppler effect. Let's put that down because we're going to define Doppler. Let's just mark it that there is no Doppler. As long as the source and the listener have the same speed, there is no Doppler. Okay. Now, I want to go to a moving. I wish I could animate this, but I need you to just visualize. I'm going to do two things. So look at this. Just going to put this in the middle. So if I decide, I want you to think of this as little rubber bands or ropes, okay, that I put as circles. If I put my finger right here and move my hand towards this, do you notice that the shape of this circle will be distorted now? Right? It no longer be concentric circles. What's going to happen? So if I decide that I want this guy to start moving in this direction, but I still want those guys to be stationary. What do you think will happen? And this is where Doppler comes in. It's going to look more like this. Okay, let me do this. Bottom layer. Move to bottom. I don't know if it makes sense. That the source, so I'm putting my hand and I'm dragging this whole thing in this direction. The source is moving in that direction. Oh, by the way, let's go back to this diagram in case you drew this diagram. I'm going to use this as my wavelength. Wavelength, wavelength. You would notice the wavelength is actually the same wavelength. The wavelength is the same across because all objects are stationary. But immediately I go to this diagram, you would notice a difference in the wavelength, and that is Doppler. This is Doppler. You would notice here I have a long wavelength as compared to the original. And at this point, I'm going to have what? A short wavelength. Because the waves are reaching listener 1 more or quickly than listener 2. Please let me know if you get this whole idea that these are called wavefronts. Wavefronts. The wavefronts are reaching listener 1 quickly. Yes, talk to me. There's a hand there. Lavi.
No, sir, I'm going to say.
Okay. The wavefronts are reaching listener 1 quicker than listener 2. I want us to write the properties on the left and on the right. Okay, so we're going to say source moves towards listener 1. All right. The wave fronts, or let me say, more wave fronts per second. More wave fronts per, let's use unit time, per unit time. If I say more, that's actually talking about the number of waves. And what will that mean? It means higher what? Frequency. And why is that? That happens because the wavelength is now, if you understand this, you are done with understanding Doppler. But as we move towards listener 1, source moves away from listener 2. Less wave fronts reach, or less wave fronts per unit time. It takes a longer time. By the time the first one reaches, then the second one, listener 1 has already heard 4. All right. So we talk about what? Very low frequency, because the number of wavefronts per unit time is small. Why is that so? The wavelength is now what? Long. Again, to let you know. And all of this is because the wave speed is constant. So the waves are not going to travel faster. They are going to travel at their own pace. So listener 2 would hear chung, chung, but listener 1 chung, 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 chung. More wavefronts. Hence a higher. Guys, please listen. We are not saying the sound is louder. We are saying the frequency is higher. Sound is only loud when the amplitude changes. We are not talking about amplitude here at all. So sound is not louder. If you understand this, then yes, we can talk about the definition of Doppler. Yes, Lavi?
Sir, would listener 2, like in some point, like hear the echo, like quote unquote echo?
Echo?
Yes.
No. Echo is the bouncing back of waves. So there is nothing reflecting the wave, so there's no echo. The wave is just passing. All right? So,
Okay, sir.
good. So echo happens when the sound bounces back. All right. So here we're just talking about frequency, the number of waves. We can then define Doppler effect now as the, okay, I know they changed it in the exam guideline, but I don't like that new definition. The word apparent is supposed to be there. But let's give them what they want. It's the what? The change in frequency observed. Please, this is very important. It is the change in frequency, like you can see there's a change in the frequency observed. So it is the change in frequency observed when there is relative motion between the listener and the source. This is the shortest correct definition. The other one I don't like it. It has too many things. Due to relative speed of sound. People forget those many words. This, you would find, this is the second definition. It's quite short and quicker. It is the change in frequency. If you don't put the word observed, you'd get a 0. Because we are looking at what is observed. And there must be relative what? Motion. Relative motion is when one is stationary and when one is moving. Here, for the first one, no relative motion. Why? They are either both stationary or both traveling at the same what? Speed. So please take note of that. If you understand this, then we are good. We can look at questions, we can look at the formula, we can jump into graphs, and I'm going to, good timing, done with Doppler in 30 minutes. But we are going to look at applications and whatnot, so come along with me. Are we good so far? Can I move to the next? Awesome. Now, let's talk about calculations. Should I talk about calculations now quickly? Yeah, let's just talk about how to use the calculations. Then we go to the graphs. Then we do examples later on. Okay. The formula. Formula and graphs. First, let's talk about variables. We're going to talk about the variables and the units. So, variables, meaning, and units, or description, whichever one. First is V. What is V? It is the speed of sound. If the examiner is dealing with outside water, then we talk about speed of sound in air. If it's in water, speed of sound in water. And this is a constant, all right? It's a constant. And the unit is meters per second. VL. This is the speed of the listener. If you notice, I am using the word speed and not velocity because we're talking about scalar. Meters per second. VS. The speed of the source. Meters per second. Now, FL is the frequency of the listener, which would be in hertz. FS, frequency of source. Also, all right, lambda L wavelength of the wave of listener. I'll show you where this one will play a role. Meters. The wavelength There's something I'm writing this for a particular purpose. I'm going to come back to that, and you're going to see where it's going to play a role. All right. So these are the variables I am using when it comes to Doppler effect. Those are the things I will be using. Now, what's important again, the formula is given, but how to use the formula is what we are going to look at again. Now, our formula, please don't write it from your head in an exam. Write it from the formula page. VL equals to V plus or minus VL, V plus or minus VS, everything multiplied by Fs. Please take note. One is moving while the other is stationary. When we get to varsity, we are going to deal with both of them moving. For now, we want to keep one moving and one stationary. And when one is stationary, what's the velocity? 0. So that's very important. Quickly, I want to break this down. If source, before I go there, sorry. Whenever we have towards or approaching, how do we know from values? Because sometimes they will not be very clear to say whether it's approaching or... This is what I wanted to look at. For something to be approaching, the frequency FL will be greater than Fs. Anytime FL is greater than Fs, like we saw earlier on, it means we have the object moving towards or approaching. The frequency of the listener higher than the frequency of the source. And your formula would be this. Formula plus and minus. All right, what do I mean by it? You would notice that we have plus or minus there, right? So when I say towards, it means I'm starting with plus and the bottom would be minus. And I'll tell you a quick way that I use to remember this. If I want to write the word towards, I'm going to start with the letter T. Do you notice that's my towards? So I don't forget. When I see approaching or towards, I know that T means a plus. It means the top is plus and the bottom is minus. Okay. So give me an example. Let's say our source is moving. Just an example. Our source is moving and listener is stationary. What's going to happen? FL would be equal to V. Because of moving, I can't just say moving. If it's moving towards, it means automatically plus. Source is moving, but the listener is stationary. This one tells me that VL equals to what? 0. Over V minus VS, and that will give me what? Fs. Case closed. We are done. That's just one formula I can move. So just get the whole idea of the formula. That's what I'm looking at. What about away? What happens? The frequency of the listener is lesser than the frequency of the source. And what will your formula be? It's the opposite. Negative on top and positive at the bottom. Negative. If you get this formula right, then case closed. This is 5 marks, 6 marks. Let's create an example. Let's say this time around, Source is stationary. Let me write example here before somebody thinks that is the only thing that happens. Example. Source is stationary and listener moving away. What will happen? V over V. Because it's away, it's a minus there and a plus there. But we said source is what? Stationary. So this would be a 0, VL. I'll tell you one thing that I usually do. The one that is stationary, I just remove it from the formula. Makes my life very easy. But I will do that when I'm looking at calculations. Guys, are we okay so far? Oh, we're doing good. I think we should be able to do quite some. I didn't have time to look for unique questions. I'm going to try to remember them. Today I want to know if I know my papers. If I can tell you Western Cape 2024, I'm going to test myself today if I know my papers. I'll try. I'll try. Because there are some unique questions. There are questions that talk about percentage. Questions that talk about decimal. We have graph questions. There are some that you have to use y equals to mx plus c to deal with. But we'll look at all of that. All right. Guys, are we okay? Are we okay? All right. We're done here. Let's look at graph. Very important. Graph at constant speed. Graph at constant speed. Towards. I'll keep repeating certain points that I want to emphasize. Graph at constant speed, or let me say graphs. Graphs at constant speed. So for example, if I have my two objects, listener and source, either way, let's say listener is moving towards the source. Whatever we talk about, as long as we mention towards, don't forget, the frequency of the listener will always be greater than the frequency of the source. But we are talking about constant speed. So when I look at the graph like this, I am going to be looking at something that looks. So first you would notice we are moving towards, then we are going to move away. I'm going to put something here. Frequency of the source. So here, let's have frequency, and here let's have time. Frequency in hertz, time in seconds. This is going to be towards, and this is going to be away. Now, both the top and the bottom are measuring frequency of the listener, frequency of the listener. And this graph will happen when the listener, constant what? Speed. Constant speed. And I want to show you something very important before we jump. We are almost done with all the notes. After this, I'll look at application, red shift and blue shift, and then we jump into calculations. Let's see if we can use 1.5 hours just to calculate. Just want to move from different types of questions. Okay. So you would not, please don't forget, the frequency of the listener is greater. So when it is towards, the frequency of the listener would be above the frequency of the source. Okay, actually I've combined. Let's just do towards and away at the same time. I mean, so it's moving towards, then moves away. So let's just, so that we don't waste time. First, let me just add a few things there. All right. And then moves away. VL is the one moving away, please. This guy is the one moving. Okay, let me do this so you don't get confused. Let's put an arrow here. Let's put an arrow here. Beautiful. So that it's very clear. At this point, the listener is moving towards and then moves away. This guy is stationary. And then here, FL. Oh, even better. We put everything together in one spot. When we're moving towards, yes, talk to me.
Sir,
Yes.
so I just wanted to ask if the video is going to be dropped on YouTube.
I'm not sure yet. Who am I speaking to?
Lucinda, sir, because I have to go somewhere right now.
Lucinda. Lucinda from Glen Vista, right?
Sir,
Where are you from? Which school are you from?
I'm from the east, from the south, sir. Old school department.
Oh, the faculty there. Up there. Okay. All right. We'll share it on YouTube for you.
Thank you, sir.
Okay. All right. Now, at constant speed, what then happens if we don't have constant speed? And I want to show you another skill you need to quickly learn in the exam. What do I mean? Let's create a scenario and then we draw the graphs. All right. Let's say listener. So this is graph number 1. Now, graphs when speed is changing. Graphs when speed is changing. And I don't want you to cram it. Please understand, constant speed, those ones are straight lines, right? Parallel straight lines, horizontal straight lines. Lovely. Let's create a scenario to say the listener is moving towards the source. And I want to teach you something, and you should be able to use this to create so that you don't cram. Listener is moving towards the source, and the speed is increasing. Don't cram. It's going to be 2 marks thereabout, but 2 marks that can be easily gotten or easily lost, because you will see the word increase or decrease, or remain the same. It will be increasing. Okay. But unfortunately, you have to put IN or DE somewhere. Okay. So this is what I'm going to show you. Look at this. Let's do a quick calculation. We said, oh, let's put this one here. Stationary what? Source. What does that tell us? Vs is equal to what? 0. If you are not sure of what to do in an exam, quickly do a calculation. I'm going to do my calculation here. We said our formula, FL equals to V. Because it's towards, it's going to be plus. Is that fine? VL, all right? and then what? Vs, Fs. Let's use the speed of sound. That will be 340. Okay, so FL will be 340. Let's say the listener is moving at the speed of 10 meters per second. Over 340 minus 0. Okay, I'm just going to create, just want to show you something. When we look at calculations, you'll understand better. Okay, let's make life easy without even a calculator. Let's say the frequency of the source is 340. Just want to make life easy. Your answer here would be 350. Because 340 over 340 would cancel. Please check something. 350. Now, at a higher speed, what will happen? FL becomes, let's change the speed to 20. This will be over 340. We keep this Fs constant. What will your answer be? 360. Do you notice that when we are moving at when the listener is moving at a faster speed, the frequency is no longer constant? The frequency has changed from 350 to 360. So your graph would look like this. Fs there. Where this graph represents FL. And this is time. Please let me know if this makes sense. Here they want to catch you, I promise you. The speed is increasing. My graph is different from the first one. Oh, why didn't I get my questions for you today? Oh, wait, I know. Please let me know if you are okay with my graph there. Take note of the difference in the graph. I'm going to quickly get some questions now so that you would see that everything I'm talking about. Guys, I'm waiting for responses. I don't think I'm seeing any. Yes, talk to me. Is that a hand for a question or you okay? Yes, talk to me. Yes, I'm listening.
So here's our speed increase. I know the person on scale now is 20.
Yep.
So if our speed increases, the frequency of the listener will increase too.
Yes, the observed frequency would increase.
All right, sir.
Can you see that it was first 350? Now it's what? 360. Because the speed is increasing. What do you think will happen if the speed is decreasing? The frequency. Yeah, go ahead, Lysander.
Isn't the frequency going to decrease?
It's going to.
Doesn't that give a sense of that the frequency and the speed are directly proportional?
Don't bring in that. I wanted to tell you, don't bring in that directly proportional. Something will be only directly proportional. Quickly learn this. If your graph is starting from the origin. But this graph is not starting from the origin. Okay?
Yes, sir.
All right. So let's draw the one of, then I'm going to ask you to draw two graphs for me now quickly. Let's draw listener moving towards the source and the speed is decreasing. So I'm going to divide this into 3. Here, listener moving towards the source, listener, source, listener is moving towards the source, but what? At a decreasing speed. That is, as you are moving towards the source, it's like let's say you're driving, there's an accident, the ambulance is already there on the road, and you are coming, and there's traffic now. What happens to your speed? It decreases. As your speed increases, frequency will also be increasing somewhere. All right. Now, I'm quickly showing you this. Don't cram. Okay? Don't cram. Quickly create a calculation for yourself. We are moving. No, it means you are creating things from the stars. Create things that human beings can. I know sometimes you think like an alien. Create things that are human, that we can relate with humanly. Okay? So, for example, look at what I'm going to do. We're moving towards, right? Remember? So, my FL will be what? By the way, this guy is what? Stationary. So, VS is equal to what? 0. Our formula will be, quickly, what will our formula be? V, it is plus on top, minus VS, VL, and FS. So, V will be 340. I'll give you some data to use for this next two. Let's say this guy is moving at 10 first. All right? And then what we have? 340 minus 0. Let's keep this as 340. What will our answer be? 350. But this guy is slowing down. This guy is slowing down. So if he's slowing down, let's change the speed to 5. Okay? I want you to see something nice here. What will our answer be? 345. Do you see what's happening? It's no longer constant because the speed is not constant. That's why if you look at most of your questions, which probably you have not been paying attention to, they will always tell you moving at constant speed. Most of us don't pay attention. What's the speed? 5. We carry on. But then multiple choice questions will have this concept for us. All right, just so you can see that the speed is decreasing. So if I were to draw a graph, I only need 2 values to see how my numbers are behaving. So as we move towards, the frequency then drops. Frequency drops. It's no longer on one straight line. It was first 350. As time increases, I'm moving slower, 345. Until I stop. And when I stop, it becomes 340. So let me see something here. Okay, it's fine. Huh? Yeah. Guys, did it make sense? Because I want to switch things around. I wanted to try. I want the source now to be moving while the listener is stationary. I want to see if you have learned the skill. It's not something you cram. You just play around with it. And you just look for 2 values to see whether it's going up or down. And you're done. I definitely need to look for a multiple choice question. Okay, let's have this. Listener and source. This guy is stationary. So VL equals to 0. Oh no, let me do something. No, let's change it. I want to maintain that. So VS is, but this guy is now moving what? Away. With an increasing what? Speed. A good example again, check. There's an accident right in front. we slow down. And I don't know what people like looking. They are checking, looking for dead people there or something. I don't understand. But immediately they pass, what happens? We start increasing our speed now, right? Good. That's what we want to see. Yeah, I don't understand. There's an accident. Pray for them and go on. No, people want to see how the tires are. Start creating questions. Yo, did you see what happened? That guy was speeding. Were you there? No, that one, he was on the phone. Aibo. Eish. Abantu. No, that guy was speeding. In fact, he was on his iPhone. It's an iPhone 15. They give the details. The guy it's telecom network. Like, really?
It was the woman.
Oh, it was the woman. She was looking for a wallet. Okay. But immediately after they passed the accident scene, yeah, you guys, you know what I'm talking about. Because sometimes I wonder, sometimes I pass a point, there's no reason for traffic. I just don't understand, but well, we are people, there's nothing we can do about people. But immediately we pass that scene, what happens? The road is now free, our speed then now what? Increases. The frequency therefore is going to change. So let's see, we are now moving away at an increasing speed. What will your graph look like? Since it's away, FL equals to V minus on top, VL over V minus VS FS. Let's create figures quickly. We're going to use 340 for V. All right, let's say we start at, hello?
Hi, sir. Isn't it that the VS at the bottom is supposed to be a plus now?
Okay, all right, okay, plus. Now, lady. Okay, all right, thank you. But it wouldn't have made a difference anyway, but it's okay, let's maintain. You'll see when I start calculating, I normally remove the one that is stationary, but all good. What's your answer here? Your answer here will be 340. My answer is 330 hertz. But check. If I then increase the speed, so I'm just moving away from the accident scene, and then I increase my speed to 40. From 10, my speed has now increased to 40. 340 plus 0, and I'm using 340 as my frequency there just to make things easy. What do you notice? My answer will be what? 300. Are we there? Can you see already? I know what my graph should look like. I already see what my graph should look like. I started from 30, and I moved to what? 300, decreasing. Although I am moving at an increasing speed, but I am moving away. Guys, I'm sure you learned the skill. You can apply it across now. So many scenarios. You learned the skill, right? So the graphs are too many to cram. Just learn the skill, put values quickly, and carry on with life. Get your 2 marks and move. And sometimes I've actually seen a question where they said they should draw the graph if the guy is increasing speed. Just put numbers and move on. All right, so can I move on from here? Can I move on from here? Okay, let's move away from here quickly. And I want us, we're still on graphs. Okay, guys, we can create any other thing. Let's look at graphs. We're still on graph. Want to do something on graph? I think this one, maybe I'll look at a question with you, but let's look at graph. All right. Using y equals to mx plus c. using y equals to mx plus c. So we're going to deal with constant speed, okay? Here, this one I remember, if I check 3 papers, I must get this question right. 3 papers, I must get this question. If I don't get it right, after checking 3, I'm going to give you something. All right, let's check. Let me explain what's going to happen here. We are going to consider listener and source. Let us consider listener moving towards the source. At constant what? Speed. The source is stationary. So Vs is equal to what? 0. All right, this time around, I don't even know my values. So let's work together. FL, since it's towards that's what we have for our formula. All right. Now, because we said the source is stationary, it's going to be 0, right? So check what we're going to do. FL will be equal to V plus VL. I normally just remove it. I hope it makes sense. Let us divide both sides by Fs. FL over Fs becomes what? V plus VL over V. And mathematically, we can then say FL over Fs is V over V. This is algebra. Splitting it. Algebra. But do you notice V over V would give us a value? That's 1. So FL over Fs is, I want to rewrite this, plus 1, because V over V is 1. Now, here is the beauty of maths. I can write this as, all right, the listener is the one moving. 1 over V multiplied by VL plus 1. Guys, I hope you understand maths here, that this will still give me this, because 1 times VL is VL. This is the beauty now. Check. Y is equal to mx plus c. On my y value, FL over Fs. On the x, VL. What will my graph look like? Beauty. Beauty. Now, what is C, by the way? Y-intercept. So that means that 1 must appear 1. In my graph, if you notice, my gradient is 1 over V, and it's positive. So it's an increasing graph. So my graph would look like this. And what I'll have on the x-axis would be what? VL. What I'll have on the y-axis would be FL over Fs. And that is 1. And the equation of this graph would simply be FL over Fs equals to 1 over V into what? VL. And that tells me that if I find the gradient m will be 1 over v. And what is v? It is the speed of sound waves. If you didn't do a question like this while you are doing Doppler, you did incomplete Doppler. I think I have about 3 different question papers where this was tested. And it's all about you knowing how to, it's a straight line. This skill that I just did here will affect almost every topic in physics. As long as there's a graph, y equals to mx plus c will be tested. So it's very, very important to expose ourselves. I'm so eager to do questions now. I'm very, very eager. But we have 2 more things to do, and then we'll look at questions. Guys, are you okay with what I'm trying to explain? When we look at questions, it's going to make more sense. I promise you. It's going to make, but get the skill. Once I see a straight line, y equals to mx plus c becomes applicable. It will make sense, I promise you. Right now, it may look like, whoo, are we doing UJ? No. We are doing your school's Doppler, whichever school you are in. We are doing the thing. All right, quickly, let me look at the 2 concepts that I have remaining. What are the concepts that I have remaining, by the way? Applications. All right, I think that's all, actually. It's only applications. And then we'll run into questions. That's where I'm going to come back again and look at all of these formulas and play around with it. All right. Applications of Doppler. What are the applications you know? I know you've done some of them. Number 1, we have medical applications. What are the medical applications? Medical, anybody who's done Doppler can tell us medical application? Yes?
The heartbeat of the fetus.
All right. And that is called ultrasound. Ultrasound to measure the heartbeat of the fetus. It's not a baby, so don't measure the heartbeat of a baby. Okay. That is one medical use, very beautiful. Second medical use. Anybody again? The blood flow meter to check for blocked veins and arteries. Because your blood vessels are supposed to actually move at a particular speed. That's when you talk about your heartbeat. Because all of those things are connected. You know, when you are sick, the first thing, don't think the nurse is just holding you. No, they are trained to quickly measure. They're counting your pulse. That is a quick way of checking. If your pulse is not regular, I think it's 72 per minute. 70, is it 72 per minute? I don't remember. But they have a way of counting. Now, what that does is it means your blood cells are supposed to be flowing at a particular speed. If there is traffic, it means one of the veins or have you ever heard of people having internal blood clotting and what? Good. Look, guys, whatever happens in you is like the highway. You're supposed to move, blood is supposed to be moving at constant speed. If there's traffic, it slows down. And when it slows down, that's one of the things that causes high blood pressure. You start breathing, your heart rate does what? It's either it's faster or slower, it means that we then need to check all your veins and whatnot. So we use the blood flow meter. I would look for a good diagram to help you see the picture. If you know these two, you're fine. Medical. All right. Let's look at another use. Astronomical use. Astronomical use or application. Let me say astronomical application. We use Doppler to check for the expanding universe. We use Doppler effect to establish that the universe is expanding. In a principle called the redshift. In a principle called the redshift. The question would be, what is redshift? Redshift is the movement of spectral lines. I'll explain this now. Towards the red end of the spectrum. Now, I actually did explain this from the beginning. When I was drawing those curves, I was actually explaining redshift. But why red? That's the question. Red is used, all right, because the red color or light is known for longer wavelength, hence low frequency. So this is what we are looking at when we look at the red shift. If you remember the diagram I had a while ago, this is going to be the Earth. And this is going to be the universe, or the galaxies, or the stars, somewhere. Stars. So you can clearly see what's happening, that we are moving away. The distance between the stars and the Earth, the galaxies, and whatnot, is expanding. Now, what are we going to observe here on the Earth? If we have the Earth eye, we are going to experience what? What are we experiencing? A long what? Wavelength. Therefore, we are experiencing low what? Frequency. And if you check your spectrum from grade 10, when we're doing Rojbiv, red has the longest what? Wavelength. That's where the word red shift comes from. It's not that we are going to see red. All right? So red shift is the movement of spectral lines towards the, I need to quickly add something there. Red end of the spectrum, let's quickly add, with long wavelength and low frequency. Red is used because the red color or light is known for longer wavelength. So as the stars are moving away, what's happening? The wavelength of what they are sending to us is increasing. That's why we call it a red shift. Guys, are we okay? And a good way to remember is this. I always say, what is the color of danger? When you see danger, what do? Run. No, don't just run. Yeah, because you can be running towards, except you are David, and danger is Goliath. Okay. But as long as you are not David and it's not David and Goliath, when you see danger, what do? You run away. And danger is known for red. Have you ever gone to the beach? Those in Joburg would not understand what I mean, though. So if you're outside Joburg, I think you understand what I mean. Yeah, those of you in Joburg, except maybe you go to the swimming. Okay, let's say swimming pool. What's the color that you see there? Kind of bluish. There's a voice that you hear. It says, come towards me. Come and enter. Blue means towards. Red means away. So if you see blue shift, it means the object is moving towards. Because blue has what? A higher frequency and a low wavelength. So please take note of the red. Are we okay here? I just want to put that red shift and blue shift. Okay, quickly as we finish now. So if I have my object here, we're moving towards. So if this is my source and this is my listener 2, remember, listener 1, this guy will be experiencing what you call what? A red shift. While this guy will be experiencing what you call what? A blue shift. And the reason for the red shift is, again, emphasis, long what? Wavelength. Low what? Frequency. While this one is experiencing what? Short what? Wavelength and high frequency. So remember, red is synonymous to danger. And this is how you remember. You run. This is where you're singing Balega. This is where you are doing Balega. Balega. Ballet. We are almost done. Just I don't want to forget things. I don't want to forget things. Okay. Spectral lines. Using spectral lines to explain red shift and blue shift. So the spectral lines are lines that are looked at from the spectrum, okay? So each element would have lines. For example, so this is a pattern. Let's look at this as a pattern of light, okay? Now, I'm going to look at this as in the universe. Or let me say, okay, I'll label that. I'll label that now. So I'm going to keep all of this as red. I'll keep this as blue. All right, this has to be the Earth. Let's call this star 1 and star 2. Reference being the Earth. Please look at my pattern very well, because the pattern is important. Pattern is very, very important. Let me shift this a bit because I want something very clear. And I have that. Then I have, okay, this one right here. This one right here. 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3. Okay, so let me see something. Let's shift this one a little bit. I want this one to be more here. All right, this is fine. This is fine. You'll be able to get what I want to show here. So you would notice the pattern. I'm maintaining the pattern. And then after this, I'll say one more thing. That one more thing is just 1 minute. And then we jump straight. We're going to do 3 types of questions. Normal questions, simultaneous questions, and graph questions. Then we're done. And you must please go and get me 15 marks here. I'll finish at 6:30. All right, guys, I wanted to look at this and I want to tell you what's going on. So look at what I have on the earth. The earth is going to be my reference point. Okay, that's what I should be seeing. But when we observe star 1, we are looking at that. I wanted to notice something here. Do you notice that this particular, let me put arrows. This particular line is the one here. The same particular line is the one. This line is this. This line is this. This line is that. What would you say has happened? They have moved towards the red side, right? So the spectral lines are shifted towards the red end. It means star 1 and star 2 are red shifted. Please, did that make sense? Star 1 and 2 are moving away because the spectral lines have shifted. The spectral lines have shifted towards the red end. So it's just observing how are the lines moving. The lines have moved towards the red, and if they move towards the red, it's just red shift, and red shift means away. Please give me thumbs up if you understand that. The lines have moved towards the red. If the lines were moving towards the blue, then we'd say it's blue shifted, which means object is moving towards. Red is away. Oh, I forgot to write here. Blue shift. Means towards. All right. The last question they'll ask you on this one. Which star is moving faster? That's huh? The first one. Why would you say the first one? It just looks right, or what? The first one is actually the correct one. And what is the reason? It is more red shifted. So it's moving away faster than the second one. So star 1 is moving at a higher speed. Star 1 is moving at a higher speed away from the earth than 2 because it is more red shifted. Guys, are we okay, please? I have one more line to write on my next slide, and we jump into calculations as quickly as possible. Guys, with your calculations, I need you to please push. The more you push, the better. I'm going to finish at 6:30 as opposed to 7. Someone is happy. The Lord is clapping. Look at everybody. They are dancing. Okay. Or can we finish at 9? All right, guys. So we'll finish at 6:30, just 1 hour. You just need to keep practicing and exposing yourselves to questions. Are we good? All right. Finally, I want to create a scenario in your head, please, and I want you to let's quickly discuss this final one. 6:45, 7:45, 5:45. We jump into questions. If an ambulance is moving towards you, an ambulance has what color? Red, right? Good. If it's moving, it will come towards you and then move away. When it's moving towards you, we said towards is blue shift. Okay, when an ambulance is coming, 2 things are being released: the sound and the light. Make sense? If I close your eyes, you can tell where the ambulance is going, whether it's moving towards you or away from you. Why? When it's moving towards you, the frequency is changing, it's higher. And then when, you can tell what I just did just by sound. What about light? Isn't it we said when it's moving towards you, we are thinking of blue. And when it's moving away, when it's moving away, we are thinking about what? A red shift. But I have watched ambulances, the color never changes. Because according to this, I think I should be seeing blue to know that it's coming, in case I'm deaf and I'm looking at light. As it's coming, I should be seeing blue, and going away, I should be seeing what? Red. The question is, why is it not changing? And that's my last statement. And here's the question I'm going to ask you. And this is examinable. Question, finally. Why is it easier to experience Doppler through sound than light? Why is it easier to experience Doppler through sound than light? Here's the answer. The relative speed of light is higher can I change where I put the word relative? The speed of light is relatively higher than the speed of sound. Relative to humans as observers. And in case you want to see it, the speed of light is 3 times 10 to the power 8 meters per second. That's 300 million from right. While the speed of sound, look at the difference, 340. These are constants. The speed of light, to make you see this value is 1, 2, 3, 4, 5, 6, 7, 8. Is it 3 million? Let me write it nicely. 8. 1, 2, 3. 1, 2, 3. That's 6, right? 7, what? 8. 6, 7. What is this? What do we have? I was right. 300. That's how fast light travels. And you can experience this even your phones. If you take a picture, the flash must go before the sound. When it's raining, people see the lightning first and they start hiding in preparation for the sound. Does that make sense? Both of them are released at the same time. But light is traveling at 3 times 10 to the power 8 meters per second. Sound, you can even, there are planes that travel faster than sound. It's called a sonic boom. If you Google sonic boom, there are these fighter jets. They travel faster than 340. So when they pass you, you'll hear the sound after it has passed. If a plane is coming, you can hear that. But these ones, when they are called sonic jets, they pass you. When you hear the sound, it has passed. And that's one of the things that they use for war. You cannot detect. By the time you hear, things have happened. Because it is traveling faster than I really want to go into one of those jets. Because I want to see how things move. When I'm traveling at 340, I want to see how fast I'm going to pass people. All right. Eh? Yeah, it's going to be. I like the way it turns around and, Okay, we're good. Even Concorde, are you sure? Michelle, are you sure? The fastest car is what? The fastest car is, there's another one that beat a Bugatti. There's a Chinese car they did that beat a Bugatti. So Bugatti is, yes, Michelle, talk to me.
No, I'm talking about Concorde, the supersonic passenger aircraft that used to get you from London to New York in 3 hours.
You sure? I need to research that.
Yes, sir. This continued in 2003.
Yeah, I know the Concorde with that long nose.
Yes, sir.
Very long nose. All right. I didn't check the speed. I've actually measured the speed of a flying plane before. Last time I like measuring the speed. I love it. I just enjoy the speed. That thing is crazy. But anyway, guys, the speed of light is relatively higher than the speed of sound relative to humans as observers. That's why we will experience Doppler easily with sound, then with light. The end of content. Questions now. All right, let's jump to questions. Guys, I have done everything that you need to do. We need to look at questions of echoes as well. We have some of those. Let's quickly look at, I just need to be very, very dynamic. Physics. Let me go to 2023. Is this physics or maths? No. Physics. Past papers. Let me go to which year? Let me try something. 2022 prelims. Let me try Free State. I'm looking for a particular paper. Okay, guys, we're gonna move as quickly as possible. There's something I'm looking for. And guys, we're not running away from multiple choice. That thing that you guys like doing, just you skip all of this and you go to question. No, please. That's not going to work for us today. It should be 1.5 or 1.6. All right, do you notice, guys, I talked about equivalent units. I spoke about equivalent units earlier on. What is the equivalent unit of what? Okay, for work energy and power or electricity, you must be able to do that. Okay, where's my Doppler? Come on. Are you telling me we don't have here? This is wave. This is object is pulled. What? Electricity. Okay. This is, oh, they put waves here as. All right, it's fine. And then, all right, there we go. Quickly, 10 marks. We're starting with this one, guys. And I'm sure we still know the formula. All right, everybody, quickly, let's start by reading. Actually, very, very good example. An ambulance moves away. Take note of that. An ambulance moves away. If I don't get my juicy questions, I'll send them later and try to do quick solutions. From an accident scene at constant speed. Its siren produces sound waves with a frequency. You see the word produces. Its siren produces. That talks about the source. Sound wave of 890. A person doing what? Standing. Stationary. Velocity is what? 0. At the accident scene, does what? Measures. The word measure is observe. A change of what? It. Please. I know you didn't see a change. You just saw a frequency of 89. They cooked many people here. All right, 89. In the frequency of the sound produced as the siren moves away. Number 1, name and describe the phenomenon. What is the name of this phenomenon? Doppler effect. Describe it, you define. I'm not going to do that, right, guys? Name is Doppler, and then we define. All right, let's check something. If the speed of sound in the air is 340, calculate the speed of the ambulance. Let's quickly write everything we have down, everybody. The ambulance moves away, so the ambulance is moving. A person is observing, and the person is standing. Let's write all the variables we have quickly. VL equals to what? 0. VS, we don't know. Speed of sound is 340. Okay, what is the movement again? Who's moving away? Okay, it's moving away, right? All right, the source is moving away. Okay, we know the frequency of the source. Now, here is the question they want to ask you. What is the frequency of the listener? Don't forget, we are moving away. When we are moving away, should the frequency of the listener, let me say, changed by 89? Which one should be higher if we are moving away? Is it the frequency of the listener or the frequency of the source? Guys, talk to me. This is where they want to. So my question is, should the frequency of the listener be higher than the frequency of the source? No, it should be lower because we're moving away. You hear it less. Let's put it that way. So what should it be the frequency of the listener? 890 minus 89. And what would that be? Does that make sense to you, everybody? And that's 1 mark. That's what they want to. That's where they want to catch you first. They want to catch people who would write 89. I think they would have caught you, Ebotile. Yeah, that one I can guarantee.
But I don't do it. I started to do it.
Okay.
Myself change.
All right. So how do you work this out, guys? We start by writing please copy the formula first. FL V plus or minus VL over V plus or minus VS. And then what? FS. We are moving what? Away, right? If we are moving away, it is minus on top. And this is what I do. Which one is stationary, by the way? VL. I just forget about it. Can you see what I did? I just forgot about it. I don't need it. It's 0. You will not be penalized for removing it. 801 equals to 340 over 340 minus VS. And what would this be? 890. Let's do the maths together, everybody. There are 2 ways of doing this maths. What I need you to see is that this one will multiply that. So I would have, let me make the maths very easy. Look at this. 340 times 890 over, you know I don't like calculators, right? So I'm going to do something. I'm going to swap both numbers. 340. Please, if you get a negative answer, just mark yourself wrong. Please, don't tell me it's the negative direction. No. Everything we are doing is scalar. So what I did here quickly is I cross multiply and I divided at the same time. Makes my life very easy. Can I ask you to get me VS, everybody? VS. Do the maths. What's your answer? Let's check. Come guys, do the maths. I need answers. You can put, what was it again? Free States 2022. That's a very good question to start with. Very good. All right, we've got a 37. Yes?
I have a question.
Yes, ask. Tata.
Did you say if it is moving away, the velocity of the listener, we're gonna minus it and then we're gonna add the velocity of the source?
If it is moving away,
and we're supposed to add the velocity of the source.
no.
Okay.
So here's the thing. Please look at your formula. This is what matters. That. I told you this. If you want to remember quickly, look at it. If it is moving towards, plus on top, minus at the bottom. Just keep it that way. So if it's towards, you'll notice the first thing I'm writing towards, it's a T. That's a plus. If I want to spell towards, it's a plus. OWA plus first. Are we good?
Yes, sir. Thank you.
Okay, guys, can I get answers? If we delay, we're not going to do so much. I'm only getting answer from Lusanda. Can we confirm that she's correct? And if you don't know what to do, you need to please let me know. The math is very, very important. So for me, what would I do? I'll move my 340 over to that side, right? Okay. And if I move the 340, what would I then get? 340 times 890 over 340. Whatever I get minus 340 is going to give me a negative.
Isn't that 01?
Oh, sorry, over 801. All right. Why is it not giving me a negative? Oh, no. No, it's a plus at the bottom. Oh, that's what you were saying. Sorry. You were right. It's negative and positive there. All right. I see what you're saying now. I made a mistake there. And that's our answer. How many marks? 5 marks. How will the frequency measured by the person be affected if the speed... Aha, check. Do you notice we're dealing with this? How will the frequency measured by the person be affected if the speed of the ambulance does what? Increases. You don't need to stress. If you already know the speed here. Are you aware that we already have this value? Right? If we put 37,78 there, we will get 801. But if this guy now increases, what happens? Your denominator becomes bigger. And when you divide with a big number, your answer becomes what? Smaller. If you are not sure, simply look, this is 1-2 marks that can boost early learner. You have 340 times 890. You have 340. We know the speed as 37,78. You're getting that. They said if the speed increases, change it to a very big number so you can see whether it's increasing or decreasing. Look at your answer, 472. So what's the answer? Decreases. Please don't just guess and lose that 1 mark. It should decrease. State one use of Doppler flow meter in the medical field. We did say that, right? To check for, they said flow meter. Doppler flow meter is to check for blocked arteries or veins. Guys, are we okay with the first question? First question is done. To check for blocked arteries or veins. Lovely. Let's run. Please, I need us to work together. Give me answers as quickly as possible. If you are not sure, there's no need to be shy. Just say, okay, I didn't get the maths. Please let us engage. Going to Mpumalanga, there's something I'm looking for. Oh, you. Okay, let's look for a multiple choice here. Where's my Doppler? Can't see, these people don't do Doppler in their district or what? 2022. What was going on? All right, it's okay. Oh, beautiful. Beautiful. We're dealing with graphs. There's something I'm looking for in one of these two districts. That's why I went straight to Mpumalanga and Free State. All right. Let's look at this together. I hope it's visible enough. You can zoom in and out. The siren of the stationary ambulance. Again, quickly. Siren is of the ambulance. All right. Emits sound wave at constant frequency. The diagram below shows a learner next to the stationary. Is it a learner? Okay, a learner. Orange tie. Nice. Stationary detector that registers the frequency of the sound emitted. The detector registers the frequency of the ambulance as the ambulance moves away at constant speed towards the learner. And no, I'm reading something different. The detector registers the frequency as the ambulance moves at constant speed towards the learner, passes him, and moves away. 3 things: towards, passes, and away. The graph below shows love this one, of the changes in detected frequencies versus time. All right. State Doppler effect. We're good. 6.2. Explain in terms of wavelength and the number of waves that reaches the detector why the observed frequency is higher when the ambulance moves. Guys, I answered this. This was where I spoke about the number of wavefronts. 6.2. They said explain in terms of wavelength and the number of waves that reaches the detector while the observed frequency is higher. Why is it higher? Observed frequency, just repeat quickly. Observed frequency as source moves towards listener is higher. And the question is, why? Reason. More wave fronts, that's the number now, per second or per unit time reaches the listener at shorter what? Wavelength. Because the distance between the waves are now small, so we can count many of them. Are we okay there, everybody? I hope it makes sense. Because the wavelength is shorter, we have more waves. Quickly. The speed of sound in air is 330. Calculate the speed of the ambulance. I love this one. 6 marks. I want us to go back and read. The siren of a stationary ambulance emits sound wave at constant frequency. Do we know the frequency? We don't know. All right. They said the diagram below shows a learner next to a stationary detector that registers the frequency of the sound emitted. All right, blah, blah, blah. The sound registers the frequency of the ambulance as the ambulance moves at a constant speed. Number 1, towards. Number 2, when it passes. Number 3, when it moves away. Guys, the graph below shows the changes in detected frequencies. It means the frequency that we have here are both frequency of listeners. Which one is higher? Towards. Which one is lower? That's why the examiner says, okay, so in this case, frequency of the source is on. Please don't say, we choose one for listener, we choose one for source. That's why you have to read carefully. The frequencies, detected frequency. Once you see the word detected, it means what? Listener. So we have 2. We know that the higher one is always towards, and the lower one is always what? Away. Guys, let's do quick maths. Can we write down the things that we have? Oh, by the way, what do we have? Nothing. What are we looking for? We're looking for speed of the ambulance. All right. This is what we do. Let's walk towards first. What's our formula? Okay, hold on. Before I say towards, what's our original formula? FL equals to what? V plus or minus VL over V plus or minus what? VS. Are we good? All right. If we are moving towards, we said it is plus on top and minus at the bottom. Which one is stationary again? The ambulance. So I know that my VS equals to what? Like I said, I just remove it from the formula. FL, towards is plus on top. So it's VL there, V. Are we good? Do I know the frequency of the listener towards? Yes. What is that? 950. Speed, please don't be used to 340. Look at the question. But do you notice I do not know that? I do not know. We're making a mistake, Robertile. Making a mistake. The diagram shows a learner next to a stationary detector. We're making a mistake. The detector registers the frequency as the ambulance moves. It is VL that is stationary. This is the detector. Please. That one is moving. So VL is stationary, please, because I could just see that something is wrong. What's our formula? VL is the stationary one, so I'm just going to remove it. Plus on top, minus at the bottom. Are we okay? Yeah, makes sense. Now, what is my FL? 950. What is my V? 330 over what? 330 minus VS. Everything multiplied by FS. Are we good? All right, here is how to deal with this one. Once I have two unknowns, this is over 1. 950 equals to 330 multiply the numerator. 330 minus VS. This is over 1. Let's cross multiply. 330 FS is 950. 330 minus VS. I'm going to stop there. Are we okay, guys? Please let me know. Let me know. I'm really hitting my target. Done one simple one. Now we are doing what? A simultaneous one. Okay. We're hitting all the targets that I want. So I am stuck here because I have two unknowns. Let's go for the away. Let's go for the away one quickly. Away. Remember, minus on top and plus at the bottom. What do we have? FL equals to V. Remember, I am simply removing my VL because it makes no difference. You are allowed to do that. Minus on top, plus at the bottom, and I have my FS. What is the frequency of the listener away? 750. 330 over 330 plus VS, and FS is unknown. Again, over 1, what do I have? 750 equals to 330 FS over 330 plus VS. Can we cross multiply? 330 FS equals to what? 750 330 plus VS. I don't know if you see what to do here. Guys, do you notice that 330 FS is this whole thing? So anywhere I see 330 FS there, I'm going to put that. And what will this be? 950 330 minus VS, because that's my 330 FS, equals to 750 330. Please do the maths and let's get VS. Everybody's working out. 6 marks. Beautiful 6 marks there. Beautiful 6 marks. Let's do the maths. All right. I'm getting 38,82 as that's the vibe I'm getting in the house. 38,8. Is there anyone who did not get 38,82 in terms of the maths? Please let me know. Otherwise, we'll take that answer as correct. Is there anyone who needs help with the maths? No one. We have one more question to do. Or two if there's time. 38,82, right? Okay, everyone seems to be okay. All right, 38,82 meters per second. Calculate the distance between the ambulance and the detector. 12,5 seconds after the detector started registering the frequency. Now it says calculate the distance between the ambulance and, now we're looking for distance. 12,5 seconds after the detector started registering. Look, what are we looking for here? The examiner is bringing in a bit of some physics, general concept. We are looking for distance. All right. And somebody saying, but there's no distance in this formula. Think beyond Doppler. What do we know? They said, calculate the distance between the ambulance and the detector. So we're talking about the ambulance. What is the speed of the ambulance, by the way? What did we get? 38,82. We are given a time frame of 12,5 seconds. What are we looking for? We are looking for the distance. Oh, easy. Distance, which is delta x. I'm sure we all know that speed equals to what? Distance divided by time. Because it's a distance between the ambulance and the detector after the detector started registering. All right, 12,5, so we're good. What's our distance? 38,82 and 12,5. Put that in a calculator and we are done. 3 point something.
One.
3,11. No. What am I doing? Am I tired? What am I looking for? I'm looking for the distance. Sorry. What is the speed? 38,82. Please cross multiply and give me an answer. I'm tired today. 38,82 times 12,5. 4. All right, there's it. We are looking for the. So please think beyond Doppler. Think physics. Make a list of the things that you have and work through. And you can also use your normal, the ones you know. You can use delta x equals to vi delta t if you want. Half a. You will get the same answer. We're looking for delta x. Our initial speed is 38,82. Time is 12,5. Acceleration is 0. Why? The ambulance is moving at constant what? Speed. You'll get the same answer. All right, so take note of that. We can use any of the two formulas. Are we good, everybody? We're good. Okay, beautiful. There's something I'm really looking for. My last chance. Don't do this to me.
I'm still in business.
Huh?
I'm still in business.
But you're not being fair.
You said 2 chances. I didn't give you an ultimatum.
Okay. Okay, just want to check. There's a particular. Okay, what's wrong with my not responding? No, you can't do this to me. What is it, 2023, right? Let's see something here. Okay, file opened already. Just make it smaller so that I can move very quickly. Just one more for the day. What province is this? Eastern Cape. No. Free State. Let's see, I need multiple choice. All right, quickly answer this multiple choice for me, everybody. Astronomers observe that the light from a distant star undergoes a red shift. Which one of the following combinations is correct for the observed wavelength and the observed frequency when compared to the wavelength and frequency of the light source? It is red shift. Red shift. Do you have your answer? Can we populate? Give me answers. Nah, am I going to mark your heart? Guys, please give me answers. Because I have to mark someone's heart here. Red, you're just quickly looking at red, what red shift is. The correct answer is B. Red shift, longer wavelength and lower frequency. Done. Thank you, guys. Look, free 2 marks there for everyone who understands Doppler. Aha. And on the third question, I hit what I want. Thank you very much.
No, you took long and you did a multiple choice before we even got there.
No, but it's the same paper.
But we did multiple choice.
Yeah,
So it doesn't count.
it counts a lot. Do you see I said Free State?
No.
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 Child.
3 questions we did a multiple choice before we even got there.
But that multiple choice was just on the way.
You were not supposed to stop on the way. You must get straight to your destination.
I wanted to give you 2 marks for free.
No.
No, so yeah, I got.
You cheated. That's not wrong.
No, I didn't cheat.
Okay, my rules.
Your rules. All right, guys, let's look at this. Let's look at this quickly. And you would notice I cannot discuss this type of questions earlier on today. So, a learner investigates the relationship between the ratio of the observed frequency to the source frequency and the velocity with which the listener moves relative to the stationary source. The experiment is repeated by increasing the magnitude of the constant speed. All right, this is not really increasing. We're just changing the speed. All right, make it constant, then change it again. With which the observer moves relative to the same stationary source. Please take note. Always let's look for that. My source is stationary. Let's write it out so that it becomes very visible when we are doing our work. The observed frequency FL is recorded. Now check, and the ratio is calculated. FL. I showed you how they got FL over FS. They divided both sides by FS. Okay. Now the graph. Do you remember this one? Okay. Question 1. State in words the phenomenon described above. State. When they say state in words, please, they ask you, they didn't say name. State, which means you define what? Doppler. Use the graph to answer the following questions. Is the learner moving towards or away? Please, if you are not sure, it's 2 marks. If you are not sure, what would you do? They said, is the learner moving towards or away? And I'll take what I did earlier. Do you notice this was what I did earlier though? So in this case, we're talking about what? Towards. And I want to quickly show you why towards. If it is towards, please check. If it is towards, the frequency of the listener should be greater than the frequency of the source. Watch this. It's very mathematical. If it is away, the frequency of the listener should be lesser than the frequency of the source. Are you with me there? Now, look at your left-hand side on the graph. FL over Fs. This value is big and this value is small. Your answer will be greater than 1. Mathematics. Put any number. 5 over 3 is 1 point something. In fact, 4 over 3. 3,1 over 3 is 1.03 because the bigger one is on top. So my FL over Fs should be above 1. Can you see your graph is above 1? What if it's away? FL over Fs, this value is big. No, sorry, that value is small because we're moving away. And this one is big. The ratio should be less than 1. And that is a good key to answer. That means if this guy was moving away, we should have had that. But because the ratio of FL over Fs is bigger than 1, it means the top is bigger than the bottom. Please, did that make sense? So I would have gotten 1 mark here and 1 mark there. Talk to me quickly. Lusanda?
Yes. So
Yes.
that makes sense because when I divide 1,05 divided by 1,00, I get a number which is 1,05. So it does make sense. Right?
Good. Which is greater than 1. So guys, please use that. Already I'm done. Is Lena moving towards? Yes, towards. Why? The ratio of FL over Fs is greater than 1. How do I know? All my values are above what? 1. Okay, so my graph here looks like that. If it was away, my graph would have looked like that. FL over Fs. It's just met here. What does the gradient of the graph represent? Now, look, here, we're not sure. You've got to quickly do what I did earlier. What do I mean you've got to do what I did earlier? If you are not sure, we are told that we are moving what? Towards. Let's run quickly. If we are moving towards, y equals to mx plus c, plus over minus. FL equals to, which one is stationary by the way? Vs. So it's going to be V. Remember, it's V plus VL. This is why I just like to remove that. Are you seeing that? Divide FL over Fs, split that, V over V plus VL over V. FL over Fs is VL over V plus 1. That's your y-intercept. So FL over Fs. What's on your x-axis? VL. Pull that out. You see, that's your x. Pull it out. What do you have? 1 over V plus 1. Y equals to what? Mx plus c. So what's your gradient? 1 over V. They said, what does the gradient of the graph represent? It is the reciprocal of the what? Speed of sound. Reciprocal means 1 over. Please talk to me, or you do the maths there and write 1 over V. Did that make sense? Did that make sense? So you can see I'm not teaching you UJ stuff. It came from Free State. There's another one like this from Pumalanga. All right. Calculate the speed of sound in air. Oh, lovely. Are they here? Oh. What is so? Why were you saying you're feeling cold? Speed of sound. Speed of sound. Child, leave me alone. Can we quickly calculate the speed of sound? What is the speed of sound? Can you see it's m? If I can get m, I'll get my speed. Let's look for the gradient together. How do you get gradient? Change in y over change in x. Let's quickly, please, everybody, and we're finishing now. We're all finishing together. 2, 2, 2. Which point can I use? Easy point. I think I can use this point and this point. Just need to know how to read your graph. 1, 0, 0, 1, 0, 1, 0, 2, and 1, what? 0, 3. Please, let's do the maths together. Let's calculate. Once we're done there, that's the only calculation in this paper, and then we're good. Let's calculate the gradient. Other questions that you see, we can send on the group. All right. Change in y over change in x. 1,03 minus 1 over 10 minus 0. Do you want to put that in a calculator for me to give me that quickly? That is 0,0103. Because we're just moving that. 0,103. But m is 1 over v. What would you do here? I'll just flip both of them, or if you want to cross multiply. Yes?
So isn't it 0,003?
0, it's Ribotile, guys. It's not me. All right, let's flip both. What do you have? V becomes what? 1 over 0,003. And what would that give you? 333,33. All right, 333, what? 33 meters per second. So guys, that's how that question would come out in the graph. And the last one, an observation of the spectrum of a distant star shows that it is moving away. Explain in terms of what? Frequency of spectral lines, how it is possible. What are they asking for? Redshift. They are simply asking for redshift. I will answer this one and we will be good. 6.5. The spectral lines shift towards the red end of the spectrum with longer, you must mention that that's where the mark is, because they said in terms of wavelength, longer wavelength and low what? Frequency. Guys, I'm going to stop here. All the content you need has been given. There's only one type of question I'm looking for, which I have to look for it and probably send it on the groups. It's a question where there's an echo. I can't remember where I'm going to find one. But I'll send about 3 or 4 questions for us to practice and also share answers with us so that it becomes easy. You know, I like to do the exact type of questions that are coming out. So we've done 3 different types today. I'll look for 3 more different types, and then your job is to look for things that look like what we have done, and you'll be able to answer your questions. All right, guys. I hope we're good. Doppler effect is done and dusted. Sweet. Have a beautiful, beautiful evening. Make sure you subscribe so that when we share, you get notified. Just look for Crazy Physics on YouTube. Once we share this lesson, you will be able to get notified. All right, have a lovely evening. Nolwazi, you on the previous screen, and there it is. Yes, Nolwazi?
Good evening, sir.
Hi, good evening.
Please, sir, please go back.
Which one? I should go back again.
Yes, please. Again.
Again?
Yes, please. Yes. Thank you, sir.
Okay, awesome. Awesome. All right. Bye, everybody. Thank you, thank you, thank you, thank you.